Hello, my name is Jim Ibenson, and today I'm going to talk about the topic of mathematics, one of the basic topics that are listed in the chapter outline. I have nothing to disclose. The objectives for this talk are just to review the keywords that surround math, essentially, within the outline that was provided. This means we're going to cover some simple mathematics. The bigger part of what we're going to talk about, though, is the second section, which is the statistics section. Because I believe that most of the questions that you get for the exams come from the statistics sections. And then there are a few computerized patient record questions, keywords that we'll briefly address, but most of those I think are students are okay on their own. First one that was really mentioned was biologic curves. And this is such a broad topic, I really wasn't sure where to go with this. Of course, I think everybody's familiar with linear curves, and these are probably the most common sort of graph that you'll end up dealing with. It's when there's just a direct relationship between two variables here, x and y. As we move up in x, y moves up a set amount each time. And this is the sort of thing that you'll use when you're doing sort of standard regression, which we'll talk about in a little bit. Now that differs from this sort of curve. This is an exponential curve. This one's showing an exponential decay. Of course, the graph could move the other direction and go this way and be an exponential growth. In an exponential curve, what really matters is the change from one time point to the other. So in this case, the change from here to here and then from here to here is the same proportion. It just continues down. And, you know, it hits some sort of a low value at some point, never really approaches zero. This is the sort of thing that you'll typically find when you're talking about different drugs. Maybe, you know, in this case, you're talking about an elimination may follow this sort of a kinetic model. And then really the final one I thought we should address is, in this case, a semi-log plot. The other one could be a log plot. In this semi-log plot, we would call it a semi because one axis is just a typical sort of 1, 2, 3, 4, where the other one moves in powers of 10. Sometimes you'll see the x-axis moving in this logarithmic scale, sometimes the y. Again, it's common to see these in pharmacodynamic sort of studies, and just the thing to realize here is that for every jump in the one, you end up going up by a power of 10 in the other, so from 10 to 100 to 1,000. Now this obviously is not all the different sorts of curves that you could cover. I think another one that you should take a few moments to look at would be a dose-response curve, a pretty simple and easy thing for them to test on a board exam. Now, moving past that and into statistics, I really think that the best way to start off with this is to divide your data into three different types. And if we think about these three different types of data, I think it makes breaking up the various statistical tests a whole lot easier. For the first case here, nominal data. This is categorical sort of data, like gender. You know, that would be one you typically say male or female, so you would call it dichotomous. It could also be things such as eye color, you know, red, blue, green, that sort of thing. Anything that can just fit into categories that we're just going to count, that's nominal data. Ordinal data is typically numerical data that has an order to it, which is why it's called ordinal, but that order, and the order means something, but the steps between the numbers may not mean the same thing. So examples. I think tumor staging or pain scores are a good example. You know, the movement from a pain score of 2 to a pain score of 3 may not be the same as a change from an 8 to a 9 for a patient. Another good example for ordinal data would be a Mallampati score. The change from a 1 to a 2 certainly isn't going to concern too many anesthesiologists, but the movement from a 3 to a 4 very well might. So there's a good example of where there is an order to it, but the difference isn't necessarily the same. Finally, scale or numerical data. This is just your typical quantitative data. It can be continuous, like age or heart rate, where, you know, 10 beats in heart rate is 10 beats in heart rate. Or it can be something discrete, like the number of pregnancies, so 1, 2, 3. In any case, each jump means the same thing. And this is the data that you'll typically deal with when you're talking about OR sort of data, but not the typical kind of data that I've seen when we're talking about testing on the board exams. Let's move now to the descriptives and thinking about those data types as we just talked about them. If you have continuous data, then means and standard deviations are usually going to be the way you're going to plot those, the way you're going to try to describe that data set. And so here we just had a whole bunch of heights. This was patients at a local hospital, and we recorded the heights. And if you plot them in this form called a histogram, you can see that it basically takes up a nice normal curve sort of distribution. The standard deviation defines the spread around that mean. You can do this with either continuous or discrete numerical data. Typically, you don't do this with ordinal data unless you have a lot of it. If you have enough samples, you can call it, you can assume that it approximates normal, but it doesn't always. And so what we usually use for ordinal data types are medians and percentiles. So the median value is where basically half the observations are going to be higher and half are going to be lower. So in this box and whisker plot, you end up seeing the median gets plotted right at this dark black line. This is the 50th percentile. And so in this case, this was for a pain score. You can see it's basically at about 4. Now, the other lines here have meanings as well. This is the 75th percentile line, the 25th percentile line. So 25% of the observations are below this line, 50% of the observations are below this line, and then 75% of the observations are below this line. And then these tails try to describe how far out the typical data goes. And so the highest of our responses is up here at the 8, although there is one outlier at value 10, and that's what the little dots would mean. So this is how you would typically describe ordinal data. Now, when we're talking about nominal data, we're usually talking about descriptions, and so these things are basically just expressed as percentages. So here we had provider level for intubation, say, divided up by practitioner, and you can see that we would express these as percentages. I want you to keep in mind, though, that if you only had one of two values, like a male-female or like a yes-no, then you would usually use specialized statistics, and we'll talk about those a little bit to come. Now, we can move from that, understanding that we're going to look at the averages or the means of these data differently. We can move from that into the different type of testing for each of those data types. So if we have that numerical continuous data, then we're going to use parametric testing. Examples would be a t-test or an ANOVA. Where if you have ordinal data or if you have that categorical data, then you're going to use what we would call non-parametric testing. And what these really mean is, are we following a normal curve or are we not following a normal curve with our data? And so common examples of a non-parametric would be a Wilcoxon test or a chi-squared test. I think the easiest thing to do when it comes to trying to learn this is just to try to memorize this table. We have things broken down here. If you just have parametric or normal data, basically meaning we have that continuous data, then these would be the various tests that you would use when trying to describe this data. If you were trying to do the same with non-parametric data, such as ordinal data like pain scores or Mallampati scores, then you would perhaps use these tests. Where if you had the binomial data, male, female, or yes-no sort of data, then this is what we would use. And I think the big thing to focus on there is if you have data that's expressed as percentages and you have two categories of it, then you're going to use the chi-square. If you have data and you're comparing groups, and you want to try to determine if the groups were different from each other in test scores or heart rate, then you would use either a paired t-test or an ANOVA. So that sits over on this side. That's where I see most of the questions for board exams coming from. Now we're going to switch gears a little bit and talk about regression. What we really mean when we talk about regression is just fitting things back to the familiar y equals mx plus b equation for a line. And basically regression works like this. Well, if we know what x is, say x might be a drug that we give, and if we know what y is, y would be the response to that drug, then we can plot all of those things across this graph, and we can try to fit that plot to a line and to figure out what our slope of that line is and what the intercept is. So here the intercept being 5. We can then test that slope for significance. Basically, if there's a slope to that line, then it has a chance to being significant. If that line's flat, then it's not significant and there's no relationship. Now we can formalize that expression in this sort of a terminology, which is typical to what you'll see when looking at various studies. Here, we have our x term, we have this beta instead of the slope is what we would use. And if we would do multiple regression, then you just end up adding more terms to it. So when we have a whole lot of factors that we're trying to use to account for, say, morbidity and mortality here at y, we would just add factors to it. Now another common test that you'll end up hearing about is logistic regression. And essentially, it's the same thing as a multiple regression. It's just if y is a dichotomous variable, like a yes or a no, then this becomes a 1 or a 0, and then we still try to fit these models to figure out what our betas are and test them. Once we've done the testing, be it with chi-squareds or with ANOVAs or with the regression, we have to figure out if our results are significant. In the case when we don't find significance, and in statistical terms that means that null hypothesis, the hypothesis that there's no difference, if we can't reject that, then we basically have to say to ourselves, did we have enough power to our study to even be able to find a difference if it existed? This is a very common topic for board exams, and it really comes to understanding what power means. So power, it's the probability that a test will reject what we would call a false null hypothesis, which means a type 2 error. Basically, we don't want to say that things are the same when they truly are different. Power increases as we do a few different things, and this is what you'll usually see. The question will revolve some way about increasing power by increasing sample size. Obviously, that's the way we typically do it. But you can also, if you can control your population that you're testing and decrease their standard deviation, or if you can increase the effect that you're trying to look for, you can increase power as well. And this equation just tries to show that in a simple way. This is one equation for calculating power based on a lot of different assumptions, so it's not something that you can use for all of them, but you can see as we change our deviation or as we change our effect size, we can end up changing the number of samples that we would need to get a powerful study. Very common sort of assumptions that you'll see for this in the real world is that people will assume that alpha is 0.05. This is that p-value that we're usually looking to try to match, and we'll put our beta at something about 0.2, and again, the beta is the probability of making that type 2 error. So we'll say we'll accept a 20% probability of that. Power is defined as 1 minus beta, so that means our power is about 80%, and that's pretty typical. And then when you're trying to design a study and trying to figure out how many samples do we need, well, then you typically will use this 0.2, 0.5, 0.8 rule, which is better described on a lot of websites if you're trying to design a study for effect size. Now, what happens if you have really, really large n's? This is something that comes up a lot. If your samples are too large, let's say you have 50,000 patients in a group, then just because you have so much power, you'll end up finding that very trivial differences can be statistically significant. And that's just because that as our n gets super high, that effect size that we need to see becomes super low. And so a really low p-value, or what we would call a good p-value, it can be due to there being a big effect or simply just having a lot of samples. This is where you have to use your clinical judgment and say, okay, perhaps that weight difference of 0.1 kilograms, even though it's statistically significant, doesn't really matter in the grand scheme of things. Now, another way to talk about effect size and to talk about whether or not your data is significant is to look at confidence intervals. And this is one of the keywords that the board wants us to address. So let's pretend we're looking at 3 different p-values. These are presented in a study. And you have a value of 0.001, you have a value of 0.03, and you have a value of 0.12. And you're trying to decide, okay, which of these is what we would call highly significant? Does the p-value tell us anything about effect strength? Well, let me pose this to you now. Let's present you with a graph. And let's say that these p-values match up with these 3 different experiments. Can we say that we know which p-value goes with which of these plots? Well, no, we can't. Because what we really need to understand is we need to know what the standard deviations were around those. And so let's pretend that this is a difference measure. I'd take an example like taking a test, a pre and a post test, and we're looking for the difference between them. And so a difference of 0 means there's no difference in whatever we did pre to post, where maybe this means they did 8 or 10 points better after whatever teaching intervention we put in there. What you can see is that this effect, because it doesn't cross 0, is going to be significant, statistically significant. This one, even though it's got the largest effect, because it was sort of an unsteady effect and it has a wide confidence interval, it crosses 0, where this one doesn't. So can we match these up with the p-values? Well, we can actually. Because this one the confidence interval is so tight on this one, even though it's a very small effect, it's highly significant. And so the p-value doesn't really tell us a whole lot about what the effect actually is. This experiment number 3 was really the one that if I was going to try to pick one, I would probably pick. The confidence interval seems reasonable. It's a good bit above 0, but I had a nice effect. And perhaps this experiment number 2 was just a little bit too unpredictable and a little bit too wide, even though it ended up having the highest of the mean effects. So confidence intervals are the way to go when it comes to describing data, and you can expect to see confidence intervals in some way, shape, or form on a board exam. Now, Bland-Altman plots are another thing that, another keyword that we were supposed to try to address, and so I just put up an example of one here. What Bland-Altman plots are is the way you can look at data when you're trying to decide if there's a difference between 2 different tests for the same thing. So in this case, we're comparing oxygen consumption from a inspired-expired gas analysis calculation versus a fit calculation. And if we figure out what our oxygen consumption is by one and figure out what is from the other and subtract the 2, if they're the same, we should get a nice line that runs right here near 0. In this case, you can see that we have a mean running at 30. And so what that means is that there's a bit of a bias to it. In this case, we get a little bit higher estimate from the gas analysis. But it seems to be pretty constant, so we can just correct that bias by adding this back in. The other thing that you'll look at with the Bland-Altman, though, is you'll look at the width right here of sort of our confidence interval. This is the mean, this line, plus 2 standard deviations. This is the mean minus 2 standard deviations. And so the smaller this range is between those two, then the better the 2 tests agree with each other. And so we have to ask ourselves, if we're going to sit within this range, so basically from minus 110 up to about 55 or so, is that difference clinically significant? And if it is clinically significant, then those 2 tests are probably not interchangeable. But if it's not significant, then perhaps those 2 tests are. That's a bit of a judgment call, not something that you can easily slap a bunch of statistics to, but this is how you interpret a Bland-Altman plot. And just to start wrapping things up in terms of statistics would come a contingency table. I tried to make this as generic as I could so that it can apply to a lot of different situations. But if you have that data that you can put into what we would call a 2x2 table, where you can put, whether or not they have a disease. So this would be yes, they have a disease. Here would be no, they do not. And this would be the question of, okay, did our screening test come up as being positive or did it come up as being negative? If you can put things in this sort of a grid, then you can calculate the sensitivity and the specificity from these equations here. You can also calculate odds ratios and risk ratios using these two equations here. Now, what are those? So they're similar, but they're not identical. The odds ratio really talks about the odds that an outcome will occur given an exposure when you compare it to people who did not have that exposure. Where the risk ratio is what we use when we're talking about an event in the two groups, in both of the two groups, I guess I should say. And so when you have something that's very rare, these are actually very similar, and they come out to be about the same, but as whatever disease we're talking about becomes more common, they diverge. And so that's usually the point that I see tested on various exams when it comes to odds ratios and risk ratios. Finally, for statistics, we talk about meta-analyses, and these are becoming more and more common through the literature as our studies become larger and larger. Meta-analyses are really used to try to combine a bunch of studies and try to figure out what their total effect is. And so you usually look at individual studies that are comparing some sort of a treatment, say, giving something for nausea during a case versus a control. And this could be a standard, or it could be just, something like saline. And you can see that each of these studies, so because their odds ratio crosses an odds of 1, which would be no difference. These ones were not statistically significant. These two were. They don't cross 1. When you're able to add up all these studies, though, then you can get a much better estimate of the real effect that's going on. And so plotting things in this sort of a plot called a forest plot, very common in meta-analyses, and meta-analyses are done to try to assemble lower-powered studies into one large-powered study. I would think that when it comes to meta-analyses, the point that will most commonly be tested would be trying to interpret this forest plot. So the way you would look at the total effect, whatever line runs right here is the sort of average effect that you found from all of these up above. And then the width here of the diamond describes the standard deviation that you get from pooling all of these together. And as I said, I thought we would mention something about the computerized patient record part. Basically, it comes down to basic computer knowledge, which most students nowadays have, honestly. And so keywords here talked about understanding the difference between programs versus operating systems. So, of course, the operating system is what sort of controls the overall computer, and a program runs within an operating system. It's knowing what a computer virus is. Essentially, it's a program that runs within the computer and makes it do things that you don't necessarily want it to do. Usually they're a bit malicious, but not always. We have to talk about, or consider, I should say, the difference between disk failure versus CPU, or central processing unit failure. So if a disk fails, you won't be able to do things like save your results. The computers can certainly act squirrely, but if you get a CPU failure, there's just going to be no calculations going on at all. The computer probably won't work at all. Then there were two other keywords mentioned, amplifiers and microprocessors. And I'm not really sure which way they would try to go with these. Amplifiers, of course, are things that take signals, something like an EKG, and try to amplify the signal enough that the computer can read it, record it, and then show it in a way that we can see it on the screen. Where microprocessors are just CPUs that are really, really small. And so the advent of microprocessors has really helped to make computers small and portable. It's allowed a bunch of the designs for the small devices that we use within the OR, but I don't think they'll ask a whole lot of specifics about microprocessor design. That wraps things up for the mathematics section. Thanks for your attention, and I hope you find this helpful.